Good. Alrighty, so quick review of the index laws. How would I go about doing these, making sure that we're showing our working and that we're not having too many issues? So 2 to the power of x minus 3 equals 32. 32 is one of those numbers that I gave you a list of that I said you should recognize. You might not know it's 2 to the power of 5, but you should at least in your head go, oh, I think that's going to be one of those powers of 2. Let me quickly check on my fingers. If you double, 2 to the power of 1 is 2, times 2 is 4, 8, 16, 32. Oh, look, I got to my fifth finger. It must be 2 to the power of 5. So I've got 2 to the power of x minus 3 is equal to 2 to the power of 5. And because the bases are the same and these two expressions are equal to each other, then the powers have to be equal. So I can say x minus 3 would have to equal 5. And I'm going to add 3 to each side and get x equals 8. And I think we were all pretty okay with that one. You might have just had a little bit of trouble reminding yourself of what to do to start off, but once you've seen that, that one shouldn't be too bad. Let's have a look at question 2. 3 to the power of a equals 27 to the power of a plus 2. So again, we've got one of these exponential equations where we're going to need to change the base to make the bases the same. And you look at 27, you go, oh, I remember 27, that's a power of 3. What power of 3 is 27? It's the third power, yeah, 3 to the power of 3. So I'm going to rewrite that. 3 to the power of a equals 3 to the power of 3. And just to be really clear, I'm going to make sure I remind myself that that entire power is a plus 2. When I've got a power raised to a power, we know from our index laws, we multiply those powers. So on the right-hand side there, I'm going to have 3 to the power of 3a plus 6, making sure I distribute that 3 to both the a and the 2, using our distributive law, which we're going to relook at this lesson, which is why we've got enough time to go and look at some of these index laws. My bases are the same. What can I say about the powers? Don't they have to equal each other? Is that what you were all calling out to me in unison there? What do I say about the powers? If the bases are the same and the two expressions are equal, they equal each other. That's lovely. You guys are full of beans for me. All right. Now I've got a linear equation I can solve. You can do it however you like. I'm going to subtract 2a from each side. I'll subtract 3a from each side to get to negative 2a equals 6. And so when I divide by negative 2, I get a equals negative 3. Third one here, 5 to the power of y equals 1 over 25. We recognize 25 as a power of 5, so I'm going to write it as 1 over 5 squared. Now we know how to move something from the denominator to the numerator when it's raised to a power. What do we do with the power? We take the negative of it. So it's going to be 5 to the power of y is equal to 5 to the power of negative 2. When I have the bases are the same and these two expressions are equal, what can I say about the powers? Oh my goodness, one of us listened and learned. Thank you. You get a gold star. Everyone else is staying in. The powers are equal. Y equals negative 2. Are we okay with that? Yes, thank you. At least I got a response from that. That's good. Thank you, Noah. And you too, Lockie. Your response. Appreciate it. Oh, a little bit tardy, Taha, but we're getting there. All right. C to the power of 3 over 2. This is interesting because all that happened with this question is people got scared because there were fractions and decided they didn't know what to do, when really you know exactly what to do. What I'm going to do as my first step is just to write this so that it looks a bit nicer, a little bit of panel beating. C to the power of 3 over 2 multiplied by the square root of c. I'm just going to call that c to the power of a half. Are you okay with that? That's what a square root is. Divided by 2c. It's usually easiest to keep working with fractions with these things. So I'm going to make my division. I'm just going to use a fraction instead. When I'm multiplying two numbers with the same base raised to powers, what do I do with the powers? Add them together. That's our first index law, isn't it? A to the power of m times a to the power of n. Add the two powers here. 3 over 2 plus a half is just 2. It's 4 halves, or 2. That was confusing people. We got a little bit scared of just adding the fractions. Once we've done that, it's fairly easy. One of the C's up top can cancel with one of the C's down the bottom, and I'm just left with C over 2. Is that okay? I'm going to just snip these out and move them to the side a little bit, these last two, because I'm running out of room to write there, and I'm going to forget what I'm writing and talking about. Oh, keeping someone up? Gee. Hope we've got time to yawn in our exam. All right. 3 f to the power of 14 times 7 f to the power of negative 5 times 2 f to the negative 2 all cubed. Well, fine, we just go left to right. Numbers times numbers, letters by letters. It's all going to work out nicely. 3 times 7, I'm going to have 21. F to the 14 times f to the negative 5. 14 plus negative 5 is f to the power of 9. I've done the first little bit there, haven't I? What I'm going to do is I'm just going to sort out the rest of this. It's being raised to the power of 3. 2 to the power of 3 is 8. Good. I'm glad no one called out 6. I was waiting for it. F to the negative 2 raised to the power of 3, multiply the powers. That's going to be f to the negative 6. Oh, again, I'm doing the same thing. Number times number, letter by letter. 8 21s, 168. F to the power of 9 times f to the negative 6. 9 plus negative 6 is 3. So it's going to be f cubed. So that was actually nice and easy, wasn't it? It's a little bit confusing because we've got numbers and letters thrown in there, but just numbers times numbers, letters by letters, it's all going to work out nicely. Lucky last, number 6. X squared, and then I want the cube root of that. I'm going to change that into index form. It's going to be much easier to work with expressions when you've got the exponent there rather than the radical sign. So the cube root is a power of a third, so I'm actually going to have x to the power of 2/3 here, all to the power of 4, and then I'm dividing by x. Now, you could keep your division sign there. It probably wouldn't matter for this one. The next little bit, some of us are still just not careful enough with multiplying a fraction by a whole number. You just multiply the numerator by numerator, denominator by denominator. 4 is the same as 4 over 1, isn't it? So I've got x to the power of 8 over 3 divided by x. So now I've got x to the power of 8/3. The denominator is 1. 8/3 minus 1, so 8/3 minus 3/3. X to the power of 5 over 3. Because in the original expression they used a radical sign, I'm going to rewrite this. Even though that's a perfectly adequate answer, I'm going to rewrite it as the cube root of x to the power of 5. You try and mirror how the question was presented to you. And they're the 6 little warm-up questions that we're going to take us a couple of minutes. So if we're still not doing those in a couple of minutes, I understand they're not the straightforward ones anymore, are they? There's a little bit more involved than just, here's a mirror example of your index law. We've got to get confident with these. If you want me to make you sheets of them, put a request in Teams. Please give me some more index law practice. I have a program that will let me write an infinite number of them for you. So that's exciting because then you can do an infinite amount of maths. Were there any other questions about those? Because I did go through them fairly quickly. If it's just a little question you don't want to take up the whole class on, yep. Yep, so here I've got C times C divided by 2 times C. And so it's good because in the exam, I did see a lot of cancelling when we shouldn't have been cancelling and some opportunities to cancel which weren't taken. What are the only things we're allowed to cancel when I'm dealing with fractions? Yeah, we can only cancel factors. When things are factorized, that means the terms are being multiplied together, or the little components of the term are being multiplied together. As long as these are being multiplied together, I could think of this as C over 2 multiplied by C over C. We all know C divided by C. What would any number divided by itself be? 1. There's a little asterisk there because 0 divided by 0 doesn't equal 1, but we'll just go with that for now. So I'm allowed to cancel the C's because they're common factors. So multiplying something by C and then dividing it by C is just going to give me what I had beforehand. So that's what we're allowed to do there. Good question. All right. Today we are looking at like terms and the distributive law and some normal expansion questions. Just have a read of that and make sure you're familiar with those things. I think you will be. I'll give you just a minute just to read it and make sure you're okay with it. All right, so we're fairly happy with those rules. We've seen them all before now a few times, right? Which ones do we need to be careful of? Some of you will need to be really careful with these perfect squares. What's the classic error that people make when we're dealing with these perfect squares? When I have a plus 4 all squared. A squared plus 16. I see that a lot, don't I?
Please don't do that.
We've got to make sure we're not doing that anymore. We don't have the opportunity to spend time having to go over that. So you just need to think about it carefully each time you're doing it. There are lots of different ways of remembering it, but we've been doing it for a long time now. So just get comfortable with it. And be aware that if that's a mistake you've made before, be aware I'm going to slow down and just concentrate when I'm dealing with these expansions. Factorizing is the reverse process of expanding using our distributive law. It's identifying common factors, writing the common factors out the front, putting the remaining factors inside the brackets. And then we go on to quadratic factoring and other things like that as well, and we've done that to death in grade 9 as well. We are just going to work through some worked examples. I'm going to do some, then I'm going to go across and you're going to do some. We will go through these fairly quickly because it is revision. I am confident you guys are going to be fine to keep up. First one here, -3 outside of x minus 5. So I distribute the -3. If it helps you to draw those lines in, draw them in. I have no problem with that. We're going to have -3x plus 15. Why is it plus 15? Because that negative distributes to both terms inside the brackets. And when I get a negative multiplied by a negative, it gives us a positive. 2x outside of 1 minus x. 2x times 1 is 2x. 2x by negative x, so I've got a positive by a negative is a negative. 2x squared. 2/7. Oh my goodness, they're getting you to deal with fractions. We can cope with that, right? 7 goes into 14 twice. That's just going to be 4x plus 6 over 7. Let's have a look at it. Make sure you're happy with that. When I go 3 times 2/7, 3 times 2 is 6. Remember, numerator times numerator. Lucky last one here. I've got 2 brackets to expand. I might need to take an extra line of working to collect my like terms. I will do that. Be careful with this negative. It needs to distribute. So I'm going to have -3x plus x squared. When I have negative x by negative x, it's giving me a positive x squared. Collecting our like terms, 3x squared minus x, take away another 3x, minus 4x. They're my ones. I'm going to bring yours a little bit close. Is it going to let me drag it a little bit closer? Four for you to try. Do them right now, please. Oh, it froze after I did it. I'm sorry. Oh, you can still see the ones you need. It's the other two. All right, are we okay with those? Do we agree with my answers?
Just keep digging.
That's pretty good. Oh no, I'm happy. It's good. She'll want her spaghetti heated up at lunchtime. She'll be happy. All right, expanding 2 brackets. What do we do? Make sure everything in the first bracket is distributed to everything in the second bracket. I'm happy for you to use the little arrows. You can draw a smiley face, a crab claw. You can use x times x plus 4 plus 5 times x plus 4. I don't really mind how you set it out. I think if you've ever had trouble with these, the best setting out is to say this first term has to multiply everything in the second bracket, plus the 5 has to multiply everything in the second bracket. Now, I don't ever set it out this way myself, but the beauty of doing it that way is if I give you something with 3 or 4 terms inside a bracket, you don't get confused, you don't end up with squiggles everywhere, and you'll always get it right. If you just went straight to this second line, x squared plus 4x plus 5x plus 20, I'm more than happy for you to go straight to that. If you were really on top of it and you went x squared plus 9x plus 20, I'd be okay with that as well. So it's up to you how much working you feel like you need to show. The alternative working, you can see it's written on the board. I'll just show you again. X plus 5 times x plus 4. When I was talking about the crab claw, that's the x distributing to each thing, the 5 distributing to each thing. See how it looks a little bit like a crab claw coming to bite you? And you get the same thing. You follow each line when you're doing the multiplication, and we're going to end up with the second line that we had above. X minus 4 all squared. I would like you to do it this way. X squared minus 2 times x times 4 plus 4 squared, only because that helps when it comes to completing the square later on. But you don't need to write it that way. If you go straight to your answer, I'm happy with that as well. But it's not a bad thing to do. If you feel you need to write x minus 4 times x minus 4 and expand them that way, that's fine as well. Question. How did I get to the, which bit? The 2 times x times 4, the bit in the middle? Yeah, so way back up here when we were looking at them, remember we had a look at these rules and we've got the a squared minus 2ab plus b squared? So I remembered my rule. But where does it come from is a good question. A minus b times a minus b. If I go a times a, I'll get a squared. A times negative b times a is also negative ab, and negative b times negative b. So every time I end up with that form. A squared minus 2 times the first thing times the second thing plus the second thing squared. So ideally, rather than having to write it side by side and do that expansion every time, you'll just remember, oh, I know what that looks like. There are other ways you can do it. I won't go into them now, but if you want to ask about those, maybe I'll come and show you. We can do it drawing a box and using a grid, and that might make it easier for some of you to see as well. The bottom one, I could go through my whole expansion, but I don't because I get excited. Why do I get excited with part C here? Difference of 2 squares. And now I don't even call it that. Do you remember what I want you to call it? Well, no, that's like if you want to call it. What is it? It's your favorite rule in maths. Have I not told you this? No. There's your best friend in maths. Who is your best friend in maths? Unit circle, we met your best friend yesterday. Your favorite rule is the difference of 2 squares because it saves you more time than any other rule between now and when you finish school. You're going to use it in trigonometry. You're going to use it in complex numbers. You're going to use it when you're completing the square. You're going to use it when we put quadratics in a turning point form. We're going to use it all the time. And if you recognize it, every time you see something plus, like a plus b, a minus b, and you know it's just the first thing squared minus the second thing squared, your life is going to be easier and you're going to save yourself so much time. Again, if you're doing that and you went straight to the bottom line, I'd be happy with that. I think it's okay to do that. But you want to recognize the rule and use that rule every time. I don't need to go through the whole expansion because I'm going to get a plus 2x and a minus 2x. They're going to cancel out. I don't need to worry about it. So recognize it and save yourself time. It gives you more time to work on the fun questions at the end of the exam. All right, you've got 3 to try on the right. I'll give you a couple of minutes. Have a go at those, please. All right, let's just check our answers, make sure we agreed. So we got x squared plus 7x plus 10, x squared minus 4x plus 4, and 9x squared minus 4. So you can see, once you know what you're doing, it's quite quick to do those. I just did them then. It took well under our 2 minutes. There's no reason why you should not be able to do these as quickly as I can, because I'm not doing anything special. Yeah. Simplify which bit further? X squareds and x's don't go together because they're not like terms. Now that I am recording, I can say that academic scholarship's not looking good. It's all right though. No one knows that I'm talking about you. Oh, I could have said it, but I didn't. Expand and simplify. Same procedure. You know how to do these ones. I don't think you need me to show you the next set. You know how to do your expansion. So straight away onto the next three on the right. If you're not sure which three, I'll put a little asterisk there. And then I'll let you have a go at the factorizing too. I think you guys need to be doing more of the maths and recalling it first. If you make an error, that's okay. I would rather you do it first and get it wrong than to ask without trying. Please have a go at them first, even if you're going to get it wrong, because it's going to then, the hypercorrection effect, it's going to help you learn and retain the information more if you've made a mistake. And if you get it right, then you're getting reinforcement that it was right anyway. So both of those are good reasons to have a go yourselves first, please.